Buenos días a todos. Bienvenidos a este ciclo internacional de conferencias virtuales Pavimentos de concreto en América, alto desempeño, durabilidad y sostenibilidad. Este es un espacio de actualización técnica que se da por invitación de la Federación Iberoamericana del Hormigón Premezclado FIP, la Cámara Colombiana del Cemento y el Concreto PROCEMCO y la International Society for Concrete Pavement ISCP. Agradecemos el apoyo de las empresas cuyo respaldo hacen posible también ofrecer este ciclo sin costo para los participantes. Ellos son Holcim, Soluciones Innovadoras y Sostenibles para la Construcción, y SICA, Construyendo Confianza. Recuerden que si durante las presentaciones tienen preguntas, pueden enviarlas por la herramienta de preguntas y respuestas QIA que se encuentra en la parte baja de sus pantallas si están en Zoom. Al final vamos a contar con un tiempo después de las 2 sesiones para tener un panel con los 2 conferencistas y darles respuestas. Si no es posible, vamos a recopilarlas y buscaremos darles respuestas por correo. Aquellos que se encuentren conectados por YouTube, hagan sus preguntas a través del chat. Bueno, esta es la segunda sesión. En la primera conocimos el panorama de los pavimentos de concreto en América Latina y algunas de las tecnologías que están transformando esta infraestructura. Hoy vamos a continuar profundizando en 2 temas que son fundamentales para el desarrollo de las carreteras del futuro: la sostenibilidad y la resiliencia. La infraestructura vial ya no puede evaluarse únicamente por su capacidad estructural. Hoy debemos considerar su impacto ambiental, el uso eficiente de los recursos, la reducción de emisiones durante su ciclo de vida y su capacidad para responder y recuperarse frente a condiciones climáticas extremas y eventos cada vez más frecuentes. Precisamente sobre estos desafíos giran las 2 conferencias que tenemos hoy. Para la primera, es un verdadero gusto darle la bienvenida al profesor Hessam Azahari, que tiene a su cargo la primera conferencia. Él va a hablarnos sobre sostenibilidad en pavimentos de concreto. Hessam Azahari es profesor asistente del Departamento de Gestión de la Construcción de la Universidad Estatal de Luisiana en Estados Unidos, donde desarrolla investigación en el campo de la sostenibilidad aplicada a edificios e infraestructura, con especial énfasis en la evaluación del ciclo de vida. Es miembro activo del American Concrete Institute, el ACI, donde lidera el Comité de Educación en Sostenibilidad y coordina desde 2017 el reconocido concurso estudiantil Ecoconcreto, promoviendo la formación de nuevas generaciones de ingenieros comprometidos con la construcción sostenible. Su trabajo académico e investigativo está orientado al desarrollo de soluciones que reduzcan el impacto ambiental de la infraestructura y fortalezcan la gestión más responsable del entorno construido. Profesora Azahari, muchas gracias por aceptar la invitación. Bienvenido a este espacio.
Thank you very much for this invitation. I'm very excited to be here to share my work and our efforts at MIT and now at Louisiana State University, where I'm working as an assistant professor to discuss what I have learned from the research and implementation efforts around life cycle assessments of the pavements. In order to start this presentation, I would like to bring this important point to your attentions about the pavement's total carbon footprint, that even in social medias and in different venues, we can see that the life cycle thinking has been started to penetrate into people's minds. Even ordinary and less technical people are very much aware of that. This is just one example that I wanted to share with you around the use of recycled materials, that it sounds great, but until you consider that it requires more construction workers to maintain it, meaning that it implies about the life cycle assessments and the amount of investments that we eventually need to consider to maintain these roads and make this road serviceable in general, and it would be able to be used by the vehicles. But how can we do that? Obviously, the approach that we recommend is considering the whole life cycle, and it's a critical approach because there are a lot of influences that pavements can have on our built environment, particularly during their long service life and their use phase. So, in addition to the materials production that you can see on the left, and it includes the impacts of, for example, raw materials extraction, emissions due to energy consumptions, and process chemistry associated with the production of, for example, Portland cement, and the amount of fuels that we need for the vehicles to build the roads, for example. We have the use-based components over the 50 to 100-year lifetime of the pavements and the interactions that pavement has with multiple parts of our built environment. And finally, the end of life, where we think about this huge amount of materials that should be demolished, but we need to think about a responsible environmental stewardship and includes that in our recycling or reusing exercises, depending on what we have locally available. But what are the use phase impacts for the pavements? If I want to summarize that into a small figure, as you can see here, it adds two major components. One part, as you can see on the right side, it's the pavement vehicle interaction effects, where the quality and the structural response of the pavements can influence the fuel consumption of the vehicles on the road. More specifically, the surface roughness of the pavements can influence the excess fuel consumption, which is induced by a rolling resistance. And on the other side, there is an excess fuel consumption that is induced by the rigidity or the stiffness of the pavements. This is very much pronounced in hot weather conditions, where we think about the sensitivity of the materials to the temperature and therefore losing the elasticity or the deformation of the pavements under the tires and when the tire meets the rubber. On the other side, we have the albedo effect, which is relevant to another property of the pavement, which is the reflectance, the surface reflectance of the pavements. So if we have a brighter pavement, we absorb less heat in our urban areas, and therefore our climate won't get much warmer. But if we have a darker surface, then we absorb more heat, and therefore the temperature goes up in urban areas. This has two different implications. The first one is much more pronounced and sensible. For example, when you think about the building energy consumptions and the amount of cooling energy for air conditioning systems, if the temperature goes up, obviously we tend to turn on the air conditioning systems more often. Therefore, we use more energy, and therefore we have more emissions associated with the production of the energy or electricity. The other part is about the reflection of the solar radiation to the top of the atmosphere, where I'm showing that here. Generally and directly, reflective pavement can send more outgoing solar radiation to the top of the atmosphere, and therefore it makes our planet cooler. It's exactly the opposite of the climate change. So if we can capture less heat, therefore we reduce the impact of the climate change. Think about it from a greenhouse gas emissions cause and effect chain on climate change. If you have more greenhouse gases, therefore you capture more heat, you trap more heat in the atmosphere, and you make our planet warmer. If you have a more reflective surface, in the same sense, you will have less heat trapped in the built environment. So now we know that pavement is not just about the materials production and construction, and over the service life, the durability, the properties like stiffness, smoothness, and surface reflectance matter a lot. How can we think about low carbon concrete pavements or low carbon pavements in general? We see that the current policies target the materials emission reduction, which we call it upfront emission reduction. But with the levers and solutions as engineers, we would be able to reduce the environmental impacts of the pavements over the life cycle much more significantly. So we can think about the mixed design, and we can think about the pavement geometrical designs in terms of the thickness of the layers or the configurations of the rebars, joint spacing, etc. And we can also think about changing our maintenance and repair schedules in the future. But the regulations are more about low carbon concrete from a materials perspective. This is really important because we definitely need to reduce the materials impact emissions. But if we only focus on materials, there are two opportunities that we lose. First, as I showed you earlier, the materials properties impact the rest of the life cycle, getting back to durability, smoothness, stiffness, and reflectance of the pavements. So if we can get a pavement less to deteriorate less faster in general, or if we have a stiffer pavements, or if we have a more reflective pavement, therefore we can definitely reduce the climate change impacts of the pavements from a life cycle perspective. And second, if we don't consider the whole life cycle, we will lose the opportunities that we can achieve in order to reduce the emissions during the use and end of life phase. If we only focus on the materials, there are a limited set of solutions replacing, for example, Portland cement with alternative or low carbon binders. But you think about how we can change our maintenance and repair schedules. How can we increase the reflectance of the pavements? Or if we can mitigate the environmental impacts by inducing circularity and improve the amount of emissions or get the credit for the end of life recycling. So the scope is broad. As you can see, there are multiple solutions, but we need the right tool to examine the effectiveness of this solution. And pavement LCA tools are developed and have been used by practitioners and researchers. But there are generally some gaps here to kind of facilitate the use of the pavement LCA for decision-making purposes. First is, as you can see, conducting pavement LCA is costly and labor-intensive. In a sense, you need to collect a lot of data, and you need a more streamlined approach with more data available to be able to overcome this issue. And also, we're talking about the next few decades of the pavement life cycle, right? Pavement is a long life product in general, speaking from an industrial ecology perspective. So thinking about the next few decades and what parameters can change and what are the ranges of uncertainty, we want to examine whether the decision and the conclusion that we have made on the environmentally preferable pavement is valid and is robust enough under the uncertainty. So we definitely need to consider a probabilistic comparative analysis among different options. So I will show you how we did it at MIT over the past decade or so of research and implementation, and I will also show you some of the examples here. We have surrogate models developed, so leveraging the power of AI, build a database to estimate the amount of roughness of the pavements. Then based on the roughness, we will design the pavements and then maintenance and repair schedule. And then instead of spending 10 minutes on software, we will only spend a fraction of a second to be able to get our results. And this is the tool that is publicly available and you're more than welcome to go and use the online tool and give us feedback. What we intentionally designed it to make the payment LCA easier for everyone in the value chain with limited information. Like there are preset values, as you can see, for example, for concrete mixed designs, asphalt mixed design based on the geographical condition and the available data, but you are still be able to change these values based on the primary data and what you already have in order to evaluate the environmental impacts. There is a design feature already embedded in the pavement LCA tool. You can either consider AASHTO 93 design, which is old design approach, or you can use mechanistic empirical design, which is more relevant and recent approach. So you can examine different design approaches and methods to design the thickness of the pavements based on the properties and the types of the materials you intend to use. You will define the maintenance and rehabilitation actions, and then it's easy to see the results. So in 3 steps, you would be able to see the results of your pavements. You can definitely refine it and get back to it and see how it changes. For example, this is a California urban interstate highways with 74,000 annual average daily traffic, around 11% truck traffic, and a 1 mile segment. We compared a hot mix asphalt, which is the red line over the life cycle, with a jointed plain concrete pavement. You can see that the concrete at the beginning, it starts higher from the embodied emissions or the materials production emissions, but because pavement stays smoother, the concrete pavement stays smoother over the course of time, we don't see any increase in a significant increase in the emissions. But for asphalt, we can see that we have a crossover after 11 years because of the significant increase in the smoothness based on the California design. You can also see the cumulative environmental impacts. The previous figure showed you the annual environmental impacts, but here, as you can see how much emissions from what part of the life cycle comes. For example, the blue part is the emissions associated with the materials production. The orange part is relevant to the pavement vehicle interactions or the excess fuel consumptions induced by the pavement properties. So for concrete, the environmental hotspot is reducing the emissions from the materials, but for asphalt, we can see that the surface roughness and deflection of the pavements matter a lot. You can also see the results in other figures and formats. You can track the International Roughness Index, IRI, as a function of time for different types of pavements. You can see the proportion of the emissions from embodied and operational or the use phase impacts over the course of time. And as I mentioned earlier, there is a great feature that you would be able to see the results probabilistically. So you can see the distribution of the outputs based on the ranges and the inputs that you have defined. So we use this tool to collaborate a lot with different states. Over the past 5 and 6 years, we had this opportunity to collaborate with some of these states like Texas DOT, Indiana DOT, and Iowa DOT. So I'm going to show you some of the examples from these DOT. The first one is the case study that we did with the Texas DOT. They wanted to evaluate how to consider an overlay on top of their continuously reinforced concrete pavements. So their option is to consider either a 4-inch CRCP or continuously reinforced concrete pavement on top of the already existing CRCP, or if you use a 2-inch hot mix asphalt on top of that. And the tool was used to evaluate the life cycle emissions. And as you can see, the CRCP option shows much lower environmental impacts owing to the benefits that it has in terms of retaining the smoothness and has a very short smoothness increase as a function of time, as opposed to hot mix asphalt that needs more frequent maintenance and repair, and you have a more significant use phase emissions in this context. The other case study that we did with the Indiana DOT was on a similar approach. They don't have continuously reinforced concrete pavements, but they are evaluating options between jointed plain concrete pavements and asphalt for reconstruction projects. The difference that we had from Texas to Indiana was that Indiana has their own observed or experimentally measured IRI data. So they, as you can see, they share the IRI data with us for different interstate road segments. And we were able to use their data to build a deterioration model for the pavements. So on the left, you can see two options that they wanted to evaluate: a 13-inch JPCP on top of a 6-inch cement-treated base. And the second options that they are currently using is a 14-inch hot mix asphalt on top of a 12-inch aggregate base. You can see the model that we have created to assess the deterioration rate of the pavement surface. The red one is hot mix asphalt. The blue one is jointed plain concrete pavements. And the dashed blue line is uncalibrated jointed plain concrete pavements IRI model that exists in Pavement ME software. And you can see that the results are slightly different between the dashed blue line and also the continuous blue line, which is the experimentally measured data from Indiana DOT. But how about the results when we compare the jointed plain concrete pavements against hot mix asphalt? The blue one is the concrete, the red one is the asphalt. Again, concrete starts larger at the beginning from an environmental impacts perspective, but because of the slower deterioration rate, we have a slighter slope when you look at this, as opposed to asphalt that has a very fast slope. So from a life cycle perspective, we see 35% reduction if you use concrete over asphalt, and the crossover point is after 24 years of the service life. So we talked a lot about the environmental impacts, but another important factor in the decision-making process with the state and local agencies are cost. So this was an important feedback that we received from multiple stakeholders, that in addition to the life cycle GHG emissions, we need to consider life cycle cost. So we put this next to each other and have a better decision, more comprehensive decision for the sustainability of the pavement. So with this new feature that we have already added to the tool, we were able to compare the cost. This is the same case study for Indiana DOT, and you can see the cost of the concrete and asphalt at the beginning is almost the same. Again, because we have lower user cost, meaning less fuel consumption from the vehicles driving on the road, then we will have a smoother increase in the cost of the pavements, concrete pavements, but we have a much faster deterioration rate and therefore user cost in the end. So as you can see, this is equal to like around 24% life cycle cost reduction, and the crossover point is after 13 years. So from a cost perspective, our turnover will be faster, and we get our investment much faster from cost saving. So these are some of the features for case studies and the options and multiple alternatives that the DOT already had in order to make a decision about whether option A is better than option B, whether concrete is better than asphalt, whether asphalt overlay is better than, for example, continuously reinforced concrete pavements. But there is an opportunity to always go above and beyond. and it's about the optimization of the pavements. As I mentioned earlier, as engineers, for example, design engineers, we have a lot of options under our control. And this could include the geometrical parameters relevant to the thickness of the layers of the pavements, the rebar sizes and the spacings for joints and also rebars, the types of the shoulder. So when we think about all these parameters, it makes it a little bit more complex to find the optimized solution. And when you consider both the cost and environmental impacts, even considering both of these objective functions make the evaluation much more complicated. But I want to show you how an optimization algorithm has helped us to reduce the emissions much more substantially. And this is a case study that we did for the state of Massachusetts. The current jointed plain concrete pavement, which is the first row, I call it business as usual. It has 15-foot joint spacing, 10-inch concrete thickness. The slab width is 12 feet, and the dowel diameter that they have used is 1.5 inch size. In the second permutation, we decreased the joint spacing from 15 to 12, but we kept the other parameters, design parameters constant. Then we reduced the thickness in addition to joint spacing in order to see if we save a little bit of more materials, meaning decreasing the thickness from 10 to 9 inches, how much environmental impacts will be saved. And then finally, we increased the slab width from 12 to 13 feet in the last case study. And here is the results for the life cycle CO2 emissions. There's always an asphalt alternative here, lower upfront emissions, but much larger use-based emissions. Then there is jointed plain concrete pavement business as usual case. If we apply the joint spacing reduction strategy, we will have a little bit of reduction in the environmental impacts. But surprisingly, when we decrease the thickness of the pavements, we saved a little bit of materials upfront, but the deterioration of the pavement was faster. So we didn't really get much benefit, and actually we had more emissions, larger emissions compared to only changing the joint spacing. And finally, by just increasing the slab width by 1 foot, we were able to have 35% reduction in the environmental impacts. And this 35% reduction changes the crossover point from 22 years to 14 years. So a substantial GHG emission reduction by just changing the design parameter. And the last case study that I would like to share with you is the Iowa DOT case. It's a state highway 57,000 ADT with the traffic growth of 2.5%, relatively larger truck percentage because it's a rural road. And their first option is 11.5-inch jointed plain concrete pavements on top of a 6-inch aggregate base. Their alternative option is 14.5-inch asphalt pavements on 12-inch aggregate base. So for the concrete, their historical parameters and documents show that they need to resurface the concrete pavements with an asphalt overlay after 33 years. In asphalt, they need to replace the top layer, so they will have a mill and fill after 20 years, and after 35 years, there's going to be an asphalt overlay. We got the data from them to calibrate the deterioration model and therefore the coefficients for estimating the IRI, cracking, faulting, so all the road distresses. And then we observed the IRI versus the analysis period based on the new calibrated model. You can easily see the impact of the maintenance and repair. For example, you can see that for the asphalt, which is the red line, after 20 years, we have a drop in the IRI. meaning that the surface was milled and filled with a new layer of asphalt. Then after 35 years, we'll have another drop, implying the asphalt concrete overlay here. But for concrete, we only have one drop because we only have a 4-inch asphalt overlay after 33 years. Here is the results when you compare the baseline versus the optimization that we have performed from two perspectives. One is we only optimize the maintenance and repair actions. So the timing and the type of the maintenance and repair based on what the DOT already had available. So nothing extraordinary and academic, but something that the DOT can already practice. So we have a 39% reduction in the environmental impacts if we only optimize the maintenance. But if we have the opportunity to both optimize the maintenance and the initial design of the pavements, then we have a substantial 44% GHG emissions reduction. From a cost perspective, optimizing both maintenance and design will reduce the life cycle cost by 12%. So this obviously looking into the pavement management systems, looking into the design parameters and maintenance and repair actions on the road can save a lot of money for the DOTs. And this is my last slide, just as a reminder that we are doing a good job. We are doing our due diligence to reduce the materials emissions, and companies and value chain stakeholders are thinking about low carbon binder system, which is the right approach to move forward. But there are other opportunities over the life cycle that we can enable by using materials and by leveraging the materials properties. And there are other solutions that we can implement during the use phase and end of life of the concrete, or in general, every type of pavement, to be able to lower the emissions. And this can only be done when we have the life cycle emissions in mind and consider the whole life cycle scope from materials, construction, use and maintenance to the end of life. With that, I would like to thank you for joining this presentation and happy to take any questions and hand it over back to Claudia.
Muchas gracias, profesor Hessam, por compartir con nosotros esta excelente presentación y por mostrarnos cómo la sostenibilidad se ha convertido en un criterio fundamental en el diseño y la gestión de los pavimentos. Las preguntas, Hessam, vamos a tenerlas después de la presentación que tenemos del ingeniero Thomas Van Damme. Entonces, nos vemos luego para la sesión de preguntas. Le damos entonces ahora paso a nuestra segunda conferencia. Nos acompaña hoy desde Michigan, en Estados Unidos, el ingeniero Thomas Van Damme, director de WJE, una de las firmas más reconocidas de Estados Unidos en consultoría e investigación sobre infraestructura. Hoy va a hablarnos sobre pavimentos de concreto resilientes. El ingeniero Van Damme es un referente internacional en pavimentos de concreto duraderos y sostenibles. Cuenta con más de 4 décadas de trayectoria en ingeniería forense, investigación y desarrollo tecnológico, liderando proyectos estratégicos para la Federal Highway Administration y participando en la elaboración de lineamientos y normativas para el uso de concretos de bajo carbono. Es Fellow del American Concrete Institute y en 2025 fue distinguido por sus contribuciones al avance de la sostenibilidad en la infraestructura. Su trabajo ha logrado convertir la investigación científica en soluciones prácticas que fortalecen la resiliencia de los pavimentos frente a los retos del cambio climático. Ingeniero Thomas, muchas gracias por acompañarnos y bienvenido a esta sesión. Puede comenzar a compartir su presentación para iniciar la conferencia.
Oh, thank you very much. And Claudia, can you see everything okay? The screen looks good?
Está viéndose muy bien. Muchas gracias, Tom. Adelante con la conferencia.
Excellent. Thank you. And Hessam, it was, I did not know you were speaking before me, but I was happy to see you and congratulations on the new position at LSU. And I was involved in that last case study. So very, very good work. My talk will follow what Hessam was just talking about, in that I will be talking about resilience with regard to concrete pavements. And looking at how we will respond to climate change, which could be brought about by our consumption and our greenhouse gas emissions. So I'll start with basically the fact that Colombia's roads must stay open. We have many challenges for Colombia, as we do around the world with the changing climate. In Colombia specifically, we have mountain terrain, steep slopes. We have very high rainfall in parts of the country that can end up producing flooding. We also have a very large coastline that will have a tendency to continue to flood as sea levels rise. Even as sea levels rise, it will lead to riverine flooding, because as the tide increases, it actually acts as a dam to the river. So the rivers back from the coast will flood for very many kilometers. And then we have many critical freight routes that are essential to Colombia's economy. And our challenge is to keep those open as the climate changes. The major challenge that we look at with flooding is going to be saturation of the supporting layers. We rely on these supporting layers to support the base and then the surface of the pavement. And as these unstabilized subgrades and base courses become saturated, they become very, very weak. So the reduction in support stiffness will result in increased stress throughout the layers and in the surface, and ultimately will compromise our structural ability to carry loads. This effect on these bases can last for many months, even after the flooding recedes. And when we put traffic back on, the roadway can be compromised, and therefore our mobility and ability to ship freight becomes compromised. Concrete pavements actually offer an excellent alternative to help mitigate some of these effects. We still have the heavy rainfall and the base saturation will occur, but concrete naturally, by the way it is designed, will spread that load out. That spreading out of the load reduces the stress in those underlying layers, and therefore we have dramatic improvement in structural capacity. So with this increase in resilience, basically this can really help maintain mobility during and immediately after flooding events. So this will obviously support our communities in a much greater fashion than if we lost our mobility. Now, there's a lot of field evidence that supports these engineering principles. Originally, when I had this slide, I had 3 continents, and now we're down to 2. But I think those of you who follow politics in the United States may consider places like Florida and Houston, Texas, maybe on a different continent and maybe planet. But that aside, there are many examples from around the world, including the 3 that I show here, in which concrete pavements have provided excellent resilience, that traffic was being able to be maintained when flooded, and even after, immediately after flooding. And so it's really essential that when we look at the engineering principles, that we see them borne out in case studies. So engineering strategies that we can apply to make pavements more flood resistant include really 5 things. One is we can improve our drainability. Drainability improvement will have limited effects where inundation occurs, where the water creeps up to and over the roadway. But in situations where there's still a place to drain water, getting the water out off the pavement and from under the pavement and out into the ditches is one really good strategy. A second strategy is to stabilize those support layers. This could be done using geosynthetic materials like geogrids, or chemically through lime stabilization, cement stabilization. So basically stiffen up and make those supporting layers less susceptible to moisture. As I mentioned, concrete pavements right in the middle is an excellent solution. So if we build concrete pavements as our new pavement type, that load gets spread out, and right By doing that, we will have excellent improvement in resiliency. As a treatment, concrete overlays are an excellent choice. Even relatively thin overlays of 3 to 4 inches over an asphalt pavement, for example, can have the same impact of spreading the load out and adding a lot more resilience. And then finally, just having good management practices where we keep track of our infrastructure and maintain it is a strategy that should be used. Now, the FHWA in the United States has done and continues to do work looking at resilient pavement systems. They more or less have come up with a resilience framework. I'll go through this in a little bit more detail in the next slide. But the bottom line is really to approach through understanding, assess the impacts, select our alternatives, implement those alternatives, and then monitor. And so illustrating that a little bit more detail, in the understanding, there are two elements to it. One is to understand where flood risks exist. And so this requires future projection, looking where flooding would be expected, both interior in the country along rivers and also along coastlines. Once you identify where the flooding occurs, at the same time, you're also looking at where your critical routes are. And so you overlay the two, those routes that are most critical to serving the community, providing access for to hospitals, to food, to employment, for freight. So you identify those two. And so basically, we look at now then the roadways, moving on to the second one, and assess how susceptible that specific vulnerable links would be to flooding. So we can evaluate the support conditions. We can look at the amount of unstabilized layers and whether if these layers get flooded, how weak they will become. And this idea is at this point, we can identify those critical links that are both going to be subjected to flooding and are critical to our economy and also are going to be vulnerable to this flooding. Once we've selected them, now we can look at solutions. The solutions that we can look at is we can compare alternatives. And if we're looking at reconstructing a link, we can bring about all of these critical elements into consideration. But one of the big ones that we'll talk about, and we have talked about, is concrete pavements. If the link is already a well-established asphalt link, and concrete overlays could be considered as an alternative. So at this point, once we've now identified our network, those critical links that are susceptible and what strategies we can use, it becomes a matter of implementing. Implementation can happen to the most critical links immediately. We can program it, or we could just know when we have to come in and do a major rehabilitation, we can implement the solution. And then finally is this idea of monitoring, where we want to make sure that whatever we do, that we monitor, that we have a good pavement management system to track performance after flooding and to see how effective we're being in mitigating the issues caused by the flooding. So building that resilient pavement system, as I mentioned, really does focus on good structural capacity. Concrete pavement provides that over various flooding conditions. We can look at providing a stiff support that could be a stabilized material. This could be cement treated or asphalt treated, but that again is not going to be susceptible to loss in stiffness due to flooding. We can implement drainage, and then we can also look at our foundation. And again, the use of stabilization techniques can really help make a soil far less susceptible to flooding. Regarding stabilization, I think this is something that is fairly easy to implement and to use more broadly if you're not already employing it. With certain clay soils, it could be a matter of stabilizing with lime, or we can also stabilize with cement. We can also use mechanical stabilization through, again, like geogrids and those type of materials. But the basic idea here is to reduce the impact of flooding, improve our durability over the long time, and this will extend life. And so it starts really with that, the base layers and moving upward. And then the idea of looking at our network and saying, we already have this very well-developed network, potentially of asphalt or even granular roadways. Those would be excellent candidates to treat with a concrete overlay. These overlays can be, as I mentioned, fairly thin. They could be as thin as 75 millimeters, or we can bring them up as thick as 150 millimeters to carry very, very heavy traffic. And it's really a very quick solution. So something like concrete overlays is something that if you're not doing them, you should be considering employing them. The bottom line is that these engineering solutions are going to work best together. So this idea of understanding the challenge, where we're going to flood, understanding that will cause our foundations to saturate and therefore making them less susceptible to saturation. We know that saturation can increase stress. Excellent application for newly constructed concrete pavement. When we look at where we know we're going to have a roadway that's going to be compromised, that could be made of materials that would be more susceptible, it's an excellent choice for a concrete overlay. And then, as mentioned, all of these things, what we're trying to do is keep our mobility going through whatever flooding event that we would experience. So circling back, what does this mean for Columbia? Basically, the freight corridors, it's really important that we keep these open. It's also extremely important that we keep communities connected to hospitals, employment, education. So recognizing where those could be compromised is that first step. We know that the mountain highways in particular are going to be very vulnerable to flooding. And we also know that coastal areas as well, immediately in the vicinity of the coast, and often where rivers come into the coast, where the rising tide will actually act as a dam and cause riverine flooding well upstream. All of these things are a challenge to us. And so, therefore, what we need to do is invest in these long-term solutions that are based on concrete. So, the key engineering lessons, we know that flooding is occurring. We also know that the changing climate is likely to bring even greater amount of flooding along coastlines and along rivers. We know that this will compromise our structural response. And so by weakening the supporting layers, and therefore we need to make very solid engineering decisions, both in looking at our drainage. This includes ditch lines, subsurface drainage, stabilization, when we're building new pavements, making sure that we stabilize those supporting layers. We should consider concrete pavement for many reasons, but one of them is to improve our resilience. We should be looking at concrete overlays as a solution to existing flexible pavements or granular pavements. And then we really need to employ this asset management to keep an eye on our network, get feedback, understand if our solutions are working, and improve. And in the end, this will create a far more reliable system. So the final takeaways are flooding is increasing and will continue to increase. Hassan talked about greenhouse gas emissions. They continue to increase, and we seem to be, even though we're using efforts to try to reduce that, we know that we're going to see a continuing change in the climate that will lead to flooding. The effect of this flooding on our structural response to the pavements is going to determine our ability to be able to use those pavements. Engineering solutions make the difference. So once we understand the flooding is going to occur and the vulnerability of our system, this is where we can employ drainage, where we can employ stabilization, concrete pavements, and overlays to really help our network have better resilience, and then track it through good asset management. And then what we want is an integrated approach. We want to make sure that we continue to collect this data bring about solutions, and improve. And in the end, these resilient pavements are going to support people in progress and economic growth. I did want to end just talking about some work that is ongoing that I'm involved with. There's going to be a new National Cooperative Highway Research Program report coming out very soon. This work has been conducted over the last few years, and it's going to be a very extensive amount of work, providing guidance on quantifying flood impacts, support in resilient design, and provide practical guidance, such as what I've talked about. Timeline on this, we're looking at basically a practical guide is going to produce, flooding impact methods. There's going to be a mechanistic empirical design framework, an implementation memo, and then there will be plenty of webinars that will be available that you could tap into. The draft guide and interim report is coming up and is due just in a few weeks, as I've been feeling a little bit of pressure there. We expect to have the revised guide completed in November and submitted to the panel, but there will be review, and then final products will show up early next year. And I would encourage you to keep an eye on this if you're interested in this topic, because this will be a very comprehensive treatment of the topic, and will show the value and the things that I've talked about, drainage, soil stabilization, and concrete pavement solutions. And so with that, there are some references and sources listed. I assume that you will have this presentation in some form available to you, so that you can get caught up on what you would need to know. And so with that, I am completed with my talk, and hopefully we have good time for questions.
Bueno, muchas gracias por la conferencia, ingeniero Tomás. Seguramente vamos a tener que hablar cuando salga ese documento para que nos lo pueda compartir. Muchas gracias al profesor Hesam y al ingeniero Tomás por estas dos excelentes conferencias que nos han permitido comprender cómo la sostenibilidad y la resiliencia se han convertido en pilares fundamentales para el desarrollo de las vías en el futuro, y cómo el concreto está apoyando y está siendo parte de estas soluciones de manera muy eficiente. Gracias también a Holcim y a SICA por haber patrocinado esta serie de conferencias. Y antes de pasar a las preguntas, quisiera dejarles a los asistentes un QR y un link donde pueden decirnos cómo les pareció la jornada de hoy, cómo estuvo la conferencia, y nos sugieran ahí también temas y expertos para futuras conferencias. Bueno, vamos a abrir entonces ahora el espacio para responder a las inquietudes de nuestros participantes. Hoy no tenemos muchas preguntas, pero vamos a darle respuesta a la que nos da. La primera de ellas nos la hace Carlos Misael Murillo. Él dice, hoy en día, ¿qué tan viable es colocar macrofibras en estos pavimentos para carreteras, y si es viable su reparación? Hesam o Tom, ¿alguno de ustedes quiere tomar?
Hesam, I can lead if you would like.
Please, that's what I wanted to ask.
Yeah, for sure. So the question that I saw was involved in the use of synthetic. It said microfibers, but I will assume that they are also considering macrofibers. When we look at the type of synthetic fiber additions that we can use in concrete pavement, generally, I have found in my own practice that a combination of synthetic microfibers and macrofibers is very helpful. The microfibers actually help early age behavior and preventing some of the plastic shrinkage cracking that can happen if we have poor weather conditions. And then the synthetic microfibers are added to really help kind of hold cracks so tightly together that they can, restrict the micro cracking from becoming macro cracking. And what we see their use most common would be in overlays. So when we have concrete overlays, it's very, very common to use a package of synthetic micro and macro fibers, and pretty easy to implement.
Ok. Gracias, Tom. Sam, ¿quieres adicionar algo a lo que dijo Tom?
Well, Tom very well described the types and the mechanism as well. I just wanted to reiterate what Tom says, because this can be a technically viable option for concrete pavements. It can improve crack control, toughness, even the post-cracking performance, which really helps us a lot to extend the service life. But the feasibility, I think, depends on the pavement type, the traffic loads, environmental conditions, particularly when we think about high traffic volume roads in hot areas. And this is where we think that we can get the most out of the use of these materials. And from a cost effectiveness perspective, we can really justify that easily.
Ok. Gracias, Hassan. Armando Sandoval, otro de nuestros asistentes, hace la siguiente pregunta. Ingeniero Hassan, cuando se refiere a la optimización de pavimentos en asfalto y que a los 35 años se coloca otra capa, acá en Colombia lo conocemos como capa de rodadura o desgaste. Por favor, acláreme esta capa que se coloca a los 35 años.
Sure, I can answer this, and Tom, because you have been pretty much involved in this project with Iowa DOT, feel free to chime in and share your thoughts. My perspective on this is more general, and what I know is that the layer applied at the year 35 to represent the rehabilitation asphalt overlay to restore the pavement surface and extend its service life. In this case, it can be interpreted that the replacement or renewal of the wearing force, and it's not an entirely new pavement structure. The exact thickness and materials properties should really correspond to the rehabilitation scenario that was defined in the analysis. So it can vary case by case, and this is something specific that we see particularly in cold climate region. I have another experience of seeing this in Quebec, in Canada, that they have already considered as a part of their pavement management systems and their asset management program, that the concrete pavement after 30, 40 years are resurfaced with asphalt.
Yeah, and what I would add is one of the interesting things that we looked at in the Iowa project was diamond grinding. And so I'm not sure if you do much diamond grinding in Colombia, but diamond grinding would allow us to work with a machine that is roughly a meter in width, and using 3 of those machines together, we can plane off a few millimeters, like, anywhere from 5 to 10 millimeters at a time of the concrete surface, and we can plane it down. And by doing so, we can restore the quality of the ride, as well as provide lots of friction, because it creates a texture that is like corduroy. And with this, we're not using new materials. And so there's a very low carbon footprint. It's only for the diesel to power the machine. And the concrete becomes very smooth and quiet. And because of that, a lot of fuel savings are implemented. And I have become a very big fan in the last, always have been a big fan of diamond grinding, but much more so in the last few years, that we should be grinding earlier and often. So if we can, on a busy roadway, if we can grind even within 10 years, we take out the initial warping that can occur as the surface dries, and then routinely grind instead of adding asphalt. And what we find is that concrete, because it's generally paved a little thicker than what we designed with to start with, and then also becomes stronger with time, we do not compromise the structural integrity. And there are pavements in California that have been in service now for 70, 75 years that have been diamond ground 5 or 6 times, and they are still in service. So diamond grinding is a excellent alternative to putting black stuff on it.
Ok, muchas gracias. Hay una pregunta de otro asistente, Sergio Nicolás Moreno. Él dice, buenos días, muchas gracias a los dos. Quisiera saber cómo se ha considerado la humedad del ambiente en los estudios realizados, ya que en Colombia tenemos zonas de altísima humedad donde paralelamente se presentan deformaciones en las vías o roturas, y si se considera que estas altas deformaciones son asociadas principalmente al diseño y proceso constructivo.
Do you want to go first, Hassam, or do you want me to?
Yeah, I'll take your crack at this, and please add whatever you think is important. I missed that as well. So thanks for the question. I think it's an interesting question, and it's one of the important design parameters in the mechanistic empirical design approach for the pavements. And environmental moisture should be considered through several factors like rainfall, drainage conditions, groundwater level, and most importantly, these will be translated into degree of saturation of the subgrade and base layers. And the moisture susceptibility of the asphalt mixture really makes things much worse in high humidity condition. But I have to say that high humidity alone is not usually the direct cause of the pavement deformation. The ponding period, meaning the prolonged moisture infiltration, really can weaken the subgrade and unbound layers. And as you can imagine, it reduces the load-bearing capacity of the pavements on the dynamic road, obviously. And then we will have easily a loss of adhesion, and cracking and rotting will be accelerated. So the severe deformations in high humidity regions like Colombia, I think is likely caused by a combination of the environmental exposure, but more importantly, inadequate drainage, material selection. As Tom showed, concrete performs much better in high humidity area. So with the structural design, considering the traffic loading and drainage system, I think this can be really overcome much more straightforward way.
And if I could, just adding on to what Hassam is saying, when I look at concrete pavements from both construction and then performance, the climate can be very important, right? So during construction, concrete likes high humidity and likes a warm temperature. That will help support its hydration and strength gain and prevent some of that early cracking. In service, where temperature can be a problem for concrete pavements is if when we joint the concrete and the joints, let's say, are not maintained, or it gets really, really hot, we can get compression at the joints and a failure known as a blow up, where the concrete pavement can actually tent upward. And that has been a problem in some US states where we've had very humid and hot weather that's been unseasonal. But we can design our concrete pavements to resist that. The one other issue for concrete pavements is that where it's dry. And I think you have some dry parts of Colombia as well, I believe on the other side of the Andes. This is going to want to make the concrete warp upward or cup upward. That will create roughness because the surface dries relative to the bottom. And so in those cases, you can diamond grind it. But for the most part, concrete is excellent over a wide range of temperatures and moisture conditions. And so it's really a great choice where you're worried about the impacts of temperature and moisture on a pavement performance.
Gracias, Tom. Les comento que para la próxima sesión, que será el próximo miércoles, estaremos hablando precisamente del fresado de pavimentos con diamante para lograr mejorar el IRI cuando hay desgaste y cuando hay diferentes cambios de nivel. Entonces, los invito a todos a participar en esta conferencia que va a ser el próximo miércoles a las 10 de la mañana, hora Colombia. Tenemos ya una última pregunta, nos la hace Carlos González. Él dice, es muy interesante toda esta tecnología de pavimentos superpuestos, el flexible y el rígido, pero creería que esto implica un aumento en costos. Para un país como Colombia, donde todavía tenemos el 90% de las vías terciarias por pavimentar, principalmente por recursos económicos, ¿realmente qué tipo de vías recomendaría esta opción de pavimentos superpuestos? Tal vez zonas industriales en grandes ciudades, carreteras primarias. ¿Cuál sería la priorización que ustedes piensan que puede darse con esta tecnología?
You want to go first again, Hassam, since you talked about life cycle costing and analysis, and then I can finish with some practical things.
Absolutely. I appreciate that. So this is a very important consideration. I think composite pavements combining flexible and rigid pavements generally involve a higher initial cost, even for concrete pavements when we look at, for example, tertiary roads, which usually bear low volume traffic. The main objective is to expand basic paved road, right, with limited resources. In Colombia, I would recommend evaluating this solution mainly for roads where traffic demand, heavy axle loads, or the economic consequence of frequent maintenance justify the additional investments. They may also be attractive for rehabilitation projects, as Tom mentioned about the overlay actions. And it can reduce the demolition construction time, heavy trafficked urban intersections. More economical alternatives like improved drainage, soil stabilization using cement treated base, for example. Surface treatments, these are what you have already locally available. So I think it provides greater overall value. And again, to my presentation points, the agencies should consider this from a life cycle perspective. This is an investment that they can have upfront, and it would pay off really fast, meaning that it will avoid any premature failures, and therefore early maintenance and repair requirements. And this saves a lot for the DOTs, as evidence showed in various states here in the US. And so making sure that the life cycle accounting mindset is already established, and they have already established life cycle costing and environmental impacts, then they can easily make a better decision that how their investments can pay off with a payback period of, for example, 10 years or so, to be able to have durable and expanded paved road network. Tom, please.
Yes, and I would add over 90% of the roads in the US are surfaced with asphalt. So we are in the exact same condition that you are, where we are trying to create good writable surfaces on our pavements with a limited budget. That said, Hassan hit on a really important thing where the economic impacts are greatest is generally where concrete pavements get used. And we see the same in the US at our urban areas, busy urban corridors. At airports, it's always the aprons and where the loads are the heaviest that end up concrete. And I would say that the final thing is, as I talked about, once you identify critical areas of your network that are susceptible to this flooding, and you may find in a very long roadway, you only have a few of these areas that could be only, a half a kilometer in length or so. Those are the areas now to do something different, to analyze those areas. And that's where you might come in and then switch from your asphalt to concrete, or use a concrete overlay to improve the resiliency. So it's a very focused approach to make the most economic sense, but also considering that life cycle that Hassam talked about. It's very important to try to get that into your thinking, not just today what it costs, but what it's going to cost us in 10 years and 20 years.
Bueno, muchas gracias a los dos, a Hesam y a Tom, por habernos acompañado el día de hoy entregándonos información de toda su experiencia y todo el trabajo que han hecho alrededor de los pavimentos. Esperamos tenerlos nuevamente con nosotros en futuras oportunidades. Y antes de terminar, quiero invitarlos formalmente a la siguiente sesión de este ciclo. Esta tercera sesión, que va a ser, como les dije, el próximo miércoles 5 de agosto a las 10 de la mañana, vamos a abordar dos temas fundamentales para lograr pavimentos de concreto con mayor desempeño y vida útil: los métodos modernos de diseño y las estrategias de mantenimiento y rehabilitación. Es ahí, en esas estrategias de mantenimiento y rehabilitación, donde hablaremos precisamente del fresado con diamante. En el chat vamos a publicar el link de registro a este ciclo para que puedan compartirlo con colegas y amigos que aún no se han unido y que estén interesados en este tema de los pavimentos de concreto. Finalmente, les recordamos nuestra invitación al 15º Congreso Iberoamericano de Pavimentos de Concreto, que se va a realizar del 30 de septiembre al 1 de octubre de 2026 en Natal, Brasil. Este va a ser un escenario ideal para continuar fortaleciendo el intercambio de experiencias entre los profesionales de Iberoamérica alrededor de los pavimentos de concreto. Para mayor información, pueden ingresar por el link que estamos publicando en el chat o simplemente escanear con su teléfono celular el QR de la imagen. Bueno, también los acompañamos los invitamos a acompañarnos este jueves, o sea, mañana, en una nueva sesión del Club Maestros del Concreto, donde continuamos aprendiendo sobre técnicas para hacer un buen concreto en obra. Nuestra labor como Prosemco incluye no solamente los profesionales, sino todas las personas que están involucradas en el trabajo de producir concretos de excelente calidad. Este es un espacio que tenemos para fortalecer conocimientos y compartir buenas prácticas que contribuyen a mejorar la calidad del concreto. Los esperamos entonces mañana jueves a las 5 de la tarde, hora de Colombia. En el chat igualmente estamos colocando el link de inscripción o simplemente accedan por el QR de la imagen. Bueno, saludamos hoy a quienes que se nos unieron por YouTube. Los invito a simplemente suscribirse a nuestro canal y recuerden todos ustedes que al cerrar esta sesión van a ser dirigidos al canal de YouTube de Prosemco, donde además van a encontrar 400 videos sobre construcción con concreto. Esta conferencia van a tenerla disponible para revivirla a partir de la próxima semana. Los invito a que se suscriban al canal, nos visiten, déjennos un like o un comentario y así crecemos esta comunidad juntos. Bueno, ya quisiera invitarlos a que se suscriban nuevamente a nuestro canal de WhatsApp de Prosemco. Es la mejor forma que tenemos de comunicarnos con ustedes. Ahí publicamos todos nuestros eventos, conferencias y capacitaciones. Unirse es sencillo, simplemente escaneen el QR de la imagen o simplemente den clic en el link que estamos publicando en el chat. Síganos en redes sociales, nos encuentran como Prosemco, estamos en X, Facebook, LinkedIn e Instagram y además, ya lo vieron, en el canal de WhatsApp. Gracias a nuestros conferencistas de hoy por compartir su conocimiento y experiencias, a nuestros patrocinadores Holcim y SICA y a todos ustedes por acompañarnos desde diferentes países en nuestra región. En nombre de la FIP, Prosemco, la ISCP, Holcim y SICA, muchas gracias por su participación. Que tengan todos un excelente día y los esperamos nuevamente la próxima semana para seguir aprendiendo de pavimentos de concreto. Gracias, Gesam. Gracias, Tom. Hasta una próxima oportunidad.
De nada.
Thank you
Feliz
so
tarde.
much for having me.
Yep.
And
Yeah, thank you.
it's great meeting you, Tom.
Ah, nice seeing you, Hassam.